Hello guys, today is the third YouTube about chapter 20 Magnetism. If you recall, in the previous YouTubes we mentioned about the wire where an electric current is passing through that wire, and when electric current is passing through a wire, then a magnetic field will be created around this wire. Today in section 20.5 we will be concerned about finding the magnitude of that magnetic field around that wire. We were talking about the direction. Today we will find out the magnitude of that magnetic field. Just to recall that section 1, 2, 3, 4 and 5 are the sections which are included in the final exam. Alright, so from 1 to 5. Now we have discussed these kind of things, and then this is all in the first 2 YouTubes, and we have discussed also the direction here, that how to do the direction of the magnetic force that is produced by the magnetic field on the current. Okay, and let me just come direct to section 20.5, which is talking about the magnetic field due to a long straight wire. So this is the same as the introductory chapter picture, and this is the current, this is the direction of the magnetic field. This is the direction, and it's in a circular path. Since we are talking about circle, it means how to recognize, like for example, the strength of the magnetic field at this point or at this point or at that point. There, for each circle there is a radius. The further you go from the wire, the weaker the magnetic field becomes. So for example, the magnetic field at this point will be stronger than the magnetic field at this point. That makes sense. The closer you are to the wire, the stronger the magnetic field is. So that gives us the conclusion that the magnetic field is inversely proportional to the radius of that circle. What about the current? The magnetic field is directly proportional to the current. The stronger the current, the stronger the magnetic field. All right. So we can put that in one kind of proportionality equation, that the magnetic field is directly proportional to the strength of the current, inversely proportional to the radius of the circle around the wire. You know that whenever we say proportional, there will be a proportionality constant. The proportionality constant at this time is mu naught over 2 pi. Mu naught over 2 pi. Where mu naught is the permeability of a free space. We mentioned the mu naught earlier. And this is the value of the mu naught that you don't, of course, have to memorize, but you need to know what is a mu naught. The mu naught is the permeability of free space. Okay, because we are talking here about free space. We're not talking about any media around the wire. All right. If you see, what is the unit of a mu naught? Tesla, meter over ampere. I want to make sure that it makes sense to you. What is the unit of the magnetic field? Tesla. What is the unit of the current? Ampere. What is the unit of the radius? Meter. So mu naught is Tesla times meter divided by ampere. Alright guys? Good. Now let's take a simple example, straightforward example about this, the magnitude of the magnetic field near to a long straight wire. When we are saying the word long, it means the length of the wire is really much longer than the radius of this circle. You know, like for example, if the radius is like 10 centimeter or even half a meter, but the length of the wire is really more than that. All right, so it is much larger than the radius of the circle. Let's see the example, and we will see how the numbers will come and how we can calculate the magnitude of the magnetic field near a long wire. This is how it is. an electric wire in the wall of a building carries a direct current of 25 ampere vertically upward. So this is the direction of the current. What is the magnitude of, what is the magnetic field due to this current at point B, 10 centimeter from the current? All right. So we want to find, you see, this is a wire in a building. It means it's a long wire. And he's asking literally the magnetic field 10 centimeter far from the wire, which is very small number. So we say the magnetic field at point B is equal mu naught over 2 pi I divided by R. What is R? You have to convert it into meter. So it's 0.10 meter, 0.1 meter. So what is the current? The current he mentioned it's 25 ampere. So you plug in the numbers and the unit is in Tesla. All right? We don't want that, the thing in Gauss. And this is right-hand rule, you know, that you can say that the current, of course, is counterclockwise. Okay? And if you say what is the direction of the current at point B, yeah, you will tell me what is, you can, you know, like at least think, what is the direction of the magnetic field at this point? You cannot say counterclockwise. He's literally saying at point B. Okay, we know that with right-hand rule number 1, your thumb is up and then the curl is counterclockwise, like this direction, okay? But if we come here, where your fingers, the curl of the finger will be going? If you do it properly, you will realize it's into the page. It's into the page. While if the same point B is 10 centimeter here, then you do again the curl and this will be out of the page. So it makes very big difference if the B is at this point from the wire or that point from the wire, because the magnetic field is the curl of your hand, which is coming out from here into here. So if this is our B, the magnetic field is out of the page. If it is at point B here, it's into the page. So you have to be careful. That is he asking in general, what is the direction of the magnetic field around the wire? Or is he asking about a specific point where you have to say it's in or out or something like that? All right. This is a simple kind of example about the calculation of the magnetic field in a point near the wire. All right. Now I want to go back before to 20.1. There is one example I would like to discuss about the very interesting example. Actually, it merged physics 1 and physics 2. Let's see what I am talking about. It says electron's path in a uniform magnetic field. Now guys, if you remember this, exactly this picture, if an electron is in the presence of a magnetic field, which is in or out of the page actually, that electron will be moving into a circular path. Okay, and that circular path is perpendicular to the direction of the magnetic field. If you see, we have discussed this in, I think, YouTube, little bit in YouTube 1, I think, but mainly in YouTube 2. So if the electron is moving like you see, it's moving, the velocity is in this direction, magnetic field is in, this is example. So basically, you know, there will be force down, so that force will keep the electron into a circular path, moving into a circular path. If you recall in physics 1, that used to be called the circular motion. The force used to be called centripetal force. If you recall, the centripetal force is ma centripetal or radial, basically we used to say, which is mv square over r. And what is r? It is the radius of the circular motion path. All right. So if you remember, if an object is moving into a circular motion, that is the force that is keeping it into that circular path is the centripetal force, which is ma, the centripetal acceleration, which is mv square r, where v is the velocity the value of the speed of that object. Now let's come to the example to understand what I am talking about. This is the same example. It says an electron is moving in a path in a uniform magnetic field. An electron travels at so and so meter per second. So he's giving you the velocity of the electron. He's giving you the velocity of the electron, okay? And it's given by that. And he's giving you also the field, the motion is perpendicular to a uniform magnetic field, and the magnetic field is so and so Tesla. All right. Basically, he is literally discussing this example that, he is discussing this example that an electron is moving and there is a uniform magnetic field and the motion is perpendicular. So basically, we are talking about this circular motion. Now, what he asks, he said, describe its path. You could say circular path, but he specified that he wants you to describe it quantitatively. It means he needs a number. It means you can say, the electron is moving into a circular path with radius so and so. All right. Let's see how we can find the radius of that kind of motion. We mentioned that since the object is moving into a circular path, so the force is equal ma, which is mv square over r. But what is the force that is causing that centripetal force or circular kind of motion? It is the force due to the magnetic field. So it's the magnetic force, which is QVB. What is a QVB? QVB sine theta, but already theta is between velocity and magnetic field, and the theta is 90 because they are perpendicular to each other, so sine theta is equal to 1. Again, if you recall in physics 1, and even if you have not taken physics 1, I am explaining it now. We have two sides of this equation in Newton's second law. This side is the mass times acceleration. This is all the forces acting on the object to cause it move. The only force that we have here on that electron is due to the presence of that electron in the magnetic field. So the force that we don't have here kind of a gravitational force. It's too small to count it. So we will just ignore it. The only force that we will count is the magnetic force. And what is the meaning of I don't want to write mg, so you will not, I will write literally magnetic. So you will not be confused about F due to the gravitational. We don't count it because electron is too small. It's there, but it's ignored, the gravitational force. So it's literally the magnetic force. If you recall, what is the magnetic force? QVB sine theta, and this is the angle which we say now that it's 90 because V and B are perpendicular to each other. So this is 1. So the magnetic force is QVB. So we say QVB is equal mass times the centripetal acceleration, which is mv square over r. 1v will go with 1v. All right. Q we have. B we have. The mass of the electron, we can get it. It's not a problem. And of course, if you are in the exam, it should be given to you either in the syllabus or in the question itself. And then the velocity he gave us, the only missing thing here is r. But I like the idea, and I really think that it is a very important idea because the motion of the electron in a uniform magnetic field is circular. So the force is equal to ma, which is mv square over r. It's going into a circular path. And the source of the force is the magnetic force, which is due to the magnetic field, which is QVB. All right. So you equal them and you find any missing information. It is a very good example to understand and to go through it. Thank you.